Good morning, calculus students. Sorry I can't be there with you today, but I have to go down and give a chapel in Illinois. So figured I would record a quick video explaining how to do the last couple of examples from our notes from lesson 4.1 on finding extreme values. So we're going to look at this expression where we're trying to find the absolute maximum and minimum values of f of x equals 3x to the 2/3 on the interval -1 to 2. So if I'm going to do this, what doesn't hurt to have a graph to help me kind of picture what's going on here. So what I'll do is I'll pull up my graphing calculator and graph that expression. 3x raised to the 2/3 power. And I'm also going to set my window so that it matches that interval. So it's on the closed interval from -1 to 2. So I'm going to, before I graph it, go to Window, set my x minimum to -1, my x maximum to +2. For a scale, 1 is probably fine. For a y minimum and y maximum, I'm going to assume that these are pretty small values, so I'll maybe go with, I don't know, -2 to 2 to start with and see what happens. Hit graph, and here comes our curve. So it looks like my +2 for a y max is not good enough, so I'm going to go back and change that to, I don't know, let's put it as high as 6. See if that'll do the trick. I graph it, and now I can definitely see the edges of the graph. So as I look at this particular graph, I am going to say that I'm willing to bet that the minimum happens right here. That's probably 0, 0, kind of like it was the example we did in class. And I'm willing to bet that the absolute maximum happens at this endpoint over here on the right side. Now on this left side, this is also going to be extreme value. I should probably list that as well, but it's probably going to be just a local maximum. Now, graphing it is one way to look at it, but we want to confirm this analytically. To do that, what we're going to do is we're going to find the derivative of the original expression and then find the zeros of that derivative or the points where that derivative is undefined. So let's get to work. As I find the derivative of 3x to the 2/3, well, using the power property, I have 2/3 going to come to the front and be multiplied by that expression. So 2/3 times 3 is 2. So that'll give me 2x raised to the -1/3 power. Now, another way that you could write that expression would be 2 over the cube root of x. That makes sense. A negative exponent goes to the bottom. Raising it to the 1/3 power is the same as taking the cube root. So 2 over the cube root of x. Well, what are the zeros of this function? So I label this as the f prime of x. Well, nothing is going to make this expression equal 0 because I have a constant in the numerator, and there's no way to make a fraction with a constant in the numerator equal to 0. However, there is a value at which this function is undefined, and that would be 0 because if I plug 0 into the denominator, I would take the cube root of 0, which is 0, which would force me to be dividing by 0, which is something I can't do. So I'm going to make a little note that this function is undefined at x equals 0. Remember, critical points are where we'll find local extremes and absolute or global extremes as well on the interior. So a critical point happens when the derivative is equal to 0 or when the derivative is undefined. Well, the derivative is undefined at 0, which means that 0 is going to be a critical point for us. So that means as I look at my graph, that guarantees that this spot right here at 0, this is definitely a critical point because my derivative is undefined right there. And that should make sense too because this looks like a cusp. So obviously our derivative is undefined at any cusp. So one thing to do is to figure it out is, looking at the graph, I'm confident that that is a minimum, absolute at that. So I will just make a little note that there's a minimum of, and then I plug in 0 into the original function. Well, 0 to a power times 3 is going to be 0. So minimum of 0 at x equals 0 is how I'd write that down. Now as far as maximum, that's the only critical point. So that means the other things I need to check that would then be the endpoints. Well, the endpoints of this particular interval are -1 and 2. -1 and 2. So I just need to figure out what's the output at those two spots. Let's plug it in. If I plug in -1, -1 to the 2/3 is going to be the cube root of -1, which is -1. Square that, you get +1 times 3 is 3. So I've got a local maximum, abbreviate real quick here, a local max of 3 at x equals -1. Now I was able to do that one in my head. Plugging in 2 is not quite as easy. 2 to the 2/3 is not something that's done in the head, so I'll check my calculator's table and figure out, well, let's see, when x is equal to 2, again, scrolling is probably not ideal, but we're just going to do this for the sake of time right now. When x equals 2, slow down, whoop, come back. You get the idea. When x equals 2, y equals 4.762, I think it said. Good enough. So that would be the maximum because there's no other points higher than that particular output on my function. So a maximum of 4.762. Pretty sure that was the decimal at x is equal to 2. So I've got all my extrema taken care of. One happened at a critical point on the interior, and the other two happened at the end points of that particular function. So we'll pause from there. We're going to pick up with another example here. I've got 1 divided by the square root of 9 minus x squared. We're told to find the extreme values. Now, in this case, we're not given a specific interval or a specific domain. So here we have to figure out the domain on our own. What x values am I going to be allowed to plug into this function? Well, first of all, I can't divide by 0. I know that. So any value that makes me divide by 0 is not going to work. In this case, if I were to plug in 3 squared is 9, and 9 minus 9 is 0. That'd be the square root of 0. That's no good. So 3 is no good. Neither is -3, because if I take -3 and square it, I also get +9. 9 minus 9 is 0, and the square root of 0 is 0, and dividing by 0 is no good. So both -3 and +3 are out. Now what's going to work? Well, I need x squared to be something that's less than 9. Because if I were to plug in, let's say 4. 4 squared is 16. 9 minus 16 is -7. You can't take the square root of a negative number either. So it's got to be numbers. The only numbers I can plug in are the ones that are in between -3 and +3. So really what I can do is I can turn this into an open interval. This is my domain. Values that are in between -3 and 3, not including -3 or 3. Open on both sides. So if I find the extreme values, again, it never hurts to have a graph to help you get an idea. So if I were to graph this particular function, we would have 1 divided by the square root of 9 minus x squared. And for my window, I know my, well, let's make this -4 so we can look at it. So we'll go -4 to 4. Scale of 1. For my y minimum, I don't think I can be 0, but I'll just leave it at -2 to 6 and see what happens. Well, there we go. There's my curve, existing from -3 to +3. Now, I'm looking for extreme values. As I look at this, I would assume that there's a maximum here and here. However, this is an open interval. I can't actually plug in -3. I can't actually plug in +3. So there's probably going to be no maximum. There's probably, looking at this, there's probably a minimum somewhere around here, probably around 0, I would bet. But let's confirm that analytically using the derivative. I'll come back to this. So finding the derivative, f prime of x is equal to, because I have a square root in the denominator, I'd treat that as a rational exponent but negative. So I'm going to treat this as 9 minus x squared raised to the -1/2 power. Okay, that'd be a square root in the denominator. So I took care of that. As I find this derivative, I will have -1/2 times 9 minus x squared raised to the now -3/2 power. So I have to subtract 1 from the exponent, times the derivative of the inside. Well, because using the chain rule, the derivative of the inside would be -2x. Now, cleaning this up, I'm multiplying all these things together. Negative times negative is going to be positive. 2 times 1/2 is going to be 1. So this is going to turn into x for a numerator with 9 minus x squared raised to the 3/2 power in the denominator. Okay, so that's my derivative. I'm supposed to figure out when is that undefined and when is it equal 0. Well, it's probably going to be undefined when I plug in 3 or -3, but remember those aren't part of my domain. I already knew I couldn't plug in 3 or -3 based on the original function. So what makes this equal 0? Well, the easiest way to think about it, this is a fraction. If I were to make the numerator equal 0, everything equals 0. So what makes x equal 0? 0 does. So I have a 0 at x equals 0. And we kind of figured that that was going to happen, that was going to be a critical point because it looked like that was the bottom of the graph right here. So what do I get if I plug in 0? That'd be the only thing to figure out. I know it's going to be a minimum. There's nothing else that's higher than that. So I just need to know the output. I'm going to have a minimum of, plug in 0. 9 minus 0 is 9. The square root of that is 3. So 1/3 is going to be our minimum. And that occurs at x, my face here, at x equals 0. No maxima to speak of because, again, we have an open interval for a domain. So hopefully that gives you a little bit of extra practice. Now, what I would say is make sure that you also do the writing assignment that's on Google Classroom. Should be pretty easy. It's just kind of taking the definitions that are in the book and turning them into your own words. So do that plus the book assignment, and we can talk again on Monday. Good luck.